All right, guys. Thank you guys all for coming out here. So this review is going to be, I'm just going to go over as much as I can. There's a lot of material, and I'm going to try to focus on chapter 15 and on or so. But I am going to try to touch on the earlier chapters just because it's pretty important stuff, and sometimes you can see those problem types show up later on. So it's a good idea to really get a good grasp on how the problem's set up. I've passed out a few review sheets, and if you guys could, after the session is over, fill those out and leave them at your seat, and I could pick them up afterwards. I've mapped this session out for the most part time-wise, but if you guys have any questions, feel free to try to stop me, and I'll try to answer a few questions here and there. But for the most part, it's just going to be me working through problems. And there's going to be a break. I'm going to set it about an hour in, and it's going to be a 10-minute break. We'll come back and finish the last 50 minutes. And what else? Oh, this is being live streamed, just so you guys are aware. And it's going to be recorded, so you guys can go back and watch it at a later date before the exam. And I will be posting the solutions for all these problems online. So if I don't get to anything, don't worry, it'll be posted. Let's see. So with that, I'm just going to go ahead and get started. All right. So with this first problem, these are kind of tricky. I feel like a lot of people had problems with them, so I just threw one in here. Main thing you always want to start with is choosing your datum, and you want to just go ahead and set the distances for all the important parts of the whatever you're looking at. So here you have XL, here's XB, and we'll just put it over here. This is going to be XM. So we have two cables here. First one is cable 1, and this one over here is cable 2. So we're going to need two different equations for each cable, or one for each cable. So for cable 1, we have XM, which is this part of the pulley, plus 3XB, which is going to account for all of this right here. And the cable stops right at this point. And that's going to be equal to a constant. And for cable 2, we have XL, which is this part right here, plus, we're looking for this part right here, so the best way to do that is just choose the longest part and then subtract this distance to get rid of all this that doesn't have the part of the cable there. So minus XB equals a constant. And we're going to take the derivative of both of those to get the velocities. So for 1, we have Vm plus 3 Vb equals 0. 2, we have 2VL plus VB equals 0. And it's going to be plus VB because if VB is moving up in terms of the velocity, it's going to be negative if it's moving up. And if B is moving up, L is going to have to be moving up. So they're going to have the same sign for velocity. So we're given that the velocity of the, this is moving at 100 millimeters per second. So that's going to be our Vm. So we can say that Vb is equal to Vm divided by 3. which gives us 100 divided by 3. And, oh, it's going to be, yeah, it's going to be negative. So it's going to come out to negative 33.3 repeating. And take that and plug that into the second cable equation. We get VL is equal to negative, or
wouldn't it be the same? The same sign?
Yeah, it would be the same. So I guess this is going to be negative because it's going to be the same. So it'll be VB over 2. And it's going to be negative 16.6, or 6 repeating, 6.7 millimeters per second, which is our A. And for our B, we have velocity of B with respect to L. So it's going to be the velocity of B minus the velocity of L. So we have B is negative 33.3 repeating minus the negative 16.67 we got for VL. That's going to be an addition, so it's equal to negative 16.6 repeating millimeters per second. And I drew a few of the diagrams already just because it's save time for these earlier problems especially. So just to cover projectile motion really quick, we have Vxo is equal to VO cos of 40, and Vyo is equal to VO sine of 40 degrees. I don't know if you guys can see on there, but the angle's going out as 40 degrees, and it's getting launched from 2 feet above ground level. This is 3.5 feet above. So in the diagram, I just put this as the ground level basically, and it's going 1.5 meters above, or feet above. And it goes a distance of 14 feet in the x direction. So for horizontal motion, we have, it's going to be uniform, so it's going to be 0 plus Vxo times the time. And at the location of B, we have x is equal to 14. The original velocity times the cosine of 40, which is that Vxo times t. And solving for, our question is looking for the initial velocity. So we're going to find two equations, and we're going to use that to solve for, we're going to have the TB that we're going to plug into this vertical motion to solve for the VO. So we have, solving for that, we have 14 over VO cos of 40, and that's equation 1. And then for vertical motion, we have y is equal to 0 plus Vy 0 times t minus 1/2 gt squared. And then at B, we have that y is equal to 1.5 feet. The original is VO sine of 40 degrees times TB minus 1/2 g TB squared. And then we're going to substitute this in to the second equation that we have. It's going to give us 1.5 equals VO sine of 40 degrees times 14 over VO cos of 40 degrees minus 1/2 g 14 over VO cos of 40 degrees. squared. And honestly, I'm not going to bother plugging it in because we're going to focus on the later stuff. So you just get VO is equal to 22.9 feet per second. And the solution will show all the numbers plugged in. So you guys can see that there. All right. Chapter 12. So for this part, we're going to start with these. This is going to be 1. We have that, from this information, we have that the acceleration of the truck is 1 meters per second squared. The acceleration of the pallet is 0.5 meters per second squared up. This is to the left. And solving for the masses from the pounds, we have 5,000 over 32.2 gives us 155.28. Mass of the actual pallet itself is 200 pounds divided by 32.2 gives us 6.211. These are all slugs. And the mass of the, the boulder, I guess, is 1,000 pounds divided by 32.2 gives us 31.056 slugs. So we have these two T's minus the MA plus MBG is equal to MA plus MB, the acceleration to A. So with all the information we have, we can plug in and solve for T. And it's going to come out to T equals 609.32. Oh yeah, so G's in there, so it'll be pounds. Then we're going to use this. This is going to be the second part.
Is that 609?
Yeah, 609, sorry. 609.32 pounds. So this is going to be the actual truck Fibri diagram. And from that, we have, we're going to focus on the horizontal direction. We have F minus T is equal to MT AT. And solving for the force, we have T plus MT AT. So these are both given. The T we just solved for. So you plug that in and you get that F is 765 pounds. And this right here is going to be for, what is it, part B. So we're looking at just these two vertical components. So we have the F force on the boulder and the pallet minus the mass of the boulder times gravity is equal to mass of the boulder times the acceleration of the boulder. And what are we solving for? The force between the boulder and the pallet, so we're solving for FAB. End up getting FAB is equal to MB AB plus G. We have all this information, so we just plug it in. And, oh, my solution cut off. Okay. It's pretty straightforward. Just plug these values in from what we saw for up here. Again, I'm just going to keep moving if that's okay with you guys, just to make sure we get to the later stuff. Here, let me plug it in. So we have MB 31.056 times AB is 0.5 plus 32.2. Yes, 1,015.53 pounds. All right. So this came out really blurry, so I'm sure you guys can't read any of that. But the question's asking, there's a 1 kilogram collar right here, and it can slide on a horizontal rod, which is free to rotate about this shaft. The collar is initially held at A by a cord attached to the shaft, right here. A spring constant, as I put it over here, K is equal to 30 Newton per meter, is attached to the collar and to the shaft and is undeformed when the collar is at A. As the rod rotates at the rate of theta dot equals 16 radians per second, the cord is cut and the collar moves out along the rod. Neglecting friction in the mass of the rod, determine A, the radial and transverse components of the acceleration of the collar at A, B, the acceleration of the collar relative to the rod at A, and C, the transverse component of the velocity of the collar at B. So we will move through that. So for the first part, we have spring force is equal to K R minus RA. And RA is the unstretched length of the spring. So since it's unstretched at the beginning, it's going to be 0 FR equals negative F SP. This is just because it's not spinning, and since these two cancel out, this is going to be 0. So AA radial 0, AA transverse 0. B, sum of the forces in the radial direction is equal to the mass times the acceleration in the radial direction. So we have negative spring force equal to the mass times R double dot minus R theta dot squared. We're going to put over here that A, acceleration of the collar relative to the rod is equal to R double dot. Pretty straightforward. That's the only way that the collar is going to be moving relative to the rod, because the rod's going to be moving with it around the shaft. So we have, this is going to be 0 is equal to M A collar rod minus 150 millimeters times 16 radians per second squared. And that's going to come out to the mass doesn't really matter because this has got to be equal to 0. So these two, this is just equal to this. So it's going to be 38,400 millimeters per second squared, or 38.4 meters per second squared. And then for C, so after the cord is cut, the only horizontal force acting on the collar is due to the spring. Thus, angular momentum about the shaft is conserved. So we have RA M of VA theta is equal to RB M VB theta, and VA theta is equal to RA theta dot 0. So we have VB theta is equal to 150 over 450 times 150 times 16 radians per second. That's going to give us 800 millimeters per second. And all right, that is our answer for the, or put it in meters per second. 800. All right. Let's see how I'm doing on time. All right. So for this one, it's pretty straightforward. We just have TA plus VA equals TB plus VB. We have TA is 1/2 MVA squared, which is going to be 0.5 over 2 kilograms times VA squared, or 0.25 VA squared. Changing the length of at A is, so it's the undeformed length is 80. Here it's going to be 150. So it's 0.15 meters minus 0.08 meters gives us 0.07 meters. So the potential energy is 1/2 K, changing L at A squared. So we have VA equals 1/2 the spring constant, Newton per meter, times 0.07 meters squared. It's going to give us 980 joules. We have, it's going to be given that at B it's going to have 0 velocity, so VB is equal to 0, so TB is equal to 0. And the length of the spring at that point is going to be this distance, so 200 millimeters. It's 2 meters minus the undeformed length gives us 0.12 meters. So potential at B is 1/2 K, changing L at B squared. VB is 1/2 400 times 10 to the third times 0.12 squared. So VB is going to be 2,880 joules. So we're going to substitute all the values that we have into here. And it's going to give us 0.25 VA squared plus 980 is equal to 0 plus 280. And solving for VA, we end up getting 87.2 meters per second. For some reason I don't have the solution to the second part, but when it eventually reaches C, all right, I'm not going to waste time trying to figure that out right now. Move on to 13.123. So it's going to be principle of impulse momentum. So the main formula we're going to use is the force of friction, and V1, so 55 miles an hour is equal to 80.667 feet per second. And we have these two values. We're looking for the shortest time that the truck can stop if the load's not going to shift. So we're going to be dealing mainly with the static friction. And using this diagram here in the x direction, so we ignore these, we have mv1 minus coefficient of static friction times the mass times gravity and the time is equal to 0, the stop condition at the end. And solving for t, it's going to be v1 over coefficient of static friction times gravity. That's going to give us t is equal to 6.26 seconds. Yeah, no problem. All right. So for this, we're looking for so this car, we're going to call this B, is moving at 2.5 miles an hour. It's going to be coupled to the stationary car, A. It's going to be at rest, has locked wheels, and this is its coefficient of friction, kinetic coefficient of friction, since it'll be moving. Determine the velocity of both the cars after the coupling is completed and the time it takes for both cars to come to rest. So this is for the first part. We have, for A, it gives us, what, 50 tons. So if you solve for that for slugs, it's going to be 3,106 slugs. For B, it's 25 tons, so it'll be 1,553 slugs. We have VA is equal to 0, and VB is given in miles an hour, and if you solve that for feet per second, it comes out to 3.6 repeating. In the left direction. So A, we have mass of B, the velocity of B is equal to the mass of A times both of their second velocity plus the mass of B and that same velocity. Solving for that velocity, we have MB VB over MA plus MB. And plugging those in, we get 2.444 feet per second. And for B, so after coupling, the friction force only acts on the first car, A, that was stationary. Since it has locked wheels, so normal force is equal to the weight. Jeez. What?
It's gonna be like that to 4.
Alrighty. So the friction force on A is going to be equal to the coefficient of static friction times the normal force on A, or coefficient of friction times the weight of A. And for B, it's going to be 0. So for the momentum, we have ma plus mb at that velocity when they start coupled, plus this force right here times the time is equal to 0. And solving for the time that it takes for them to stop, we have ma plus mb times that over fa. That's going to be mb over that. So we get t is equal to 1553 over 3.667 over 0.30 times 100,000 pounds. And it's going to be equal to 0.1898 seconds.
Seconds?
0.1898. All right. All right. Let's see how many of these we have. All right, I'm gonna skip this 14.4 so I can try to get, before the break, I'm gonna try to get through 15. So I'll just touch these two because they're pretty important. I don't know if you guys can see this, but this A right here is on the z-axis. And it's going to be 3 feet from the x-axis, and it's going to be, so it's the only position for it is going to be 3K. There's a B that's right here. It's also 3 feet from the x-axis, but it's also up 2 feet in the y direction. So we have 2I. Oh, and it's also, what? Oh yeah, 2 feet along the x-axis. So we have 2I plus 2J plus 3K. And there's a C that's up here. And it is 1 feet along the x-axis and 4 feet above the z and x along the y-axis. So we have I plus 4J. Man, it's really blurry. Sorry. All right. So the masses of all of the particles are 19.32 pounds, which I'm just going to say m is equal to 0.6 slugs. And we're looking for, okay, so we have that the angular momentum is negative 1.2 in the k direction. We're looking for the velocities of all the particles, the angular momentum, and the angular momentum of the system about its mass center g. So for A, velocities are part of this, so we're going to basically solve for this and then use it to solve for the velocities. So we have, I'm just going to go up here since I have some room. We have HO equals negative 1.2k. And then formula is RA cross MAVA plus RB cross MB VB plus RC cross MC VC. That's going to be equal to, I'll just do this real quick. So 0.03, 0.6 VA, 0. One, 4, 0, 0.6 VC. So we get negative 1.8 VAI plus 1.8 VBJ minus 1.2 VBK plus 2.4 VCI minus 0.6 VCI, or VCJ, sorry. So you have negative 1.8 VA plus 2.4 VC in the I plus 1.8 VB minus 0.6 VC in the J plus negative 1.2 VB in the K. And that's going to be equal to negative 1.2K. So we have these two as being equal. So we know that you can take that VB is going to be equal to 1 feet per second. And we know that these two have to cancel out. So if we plug in VB into this, you guys can see, we get that VC is equal to 3 feet per second. And with that, we can plug that into this, since this has to equal 0. And we get that VA is equal to 4 feet per second. So that's our part A. And for part B, we have, so the coordinates of the mass center G in feet is MA RA plus MB RB plus MC RC all over the sum of the masses. So we have 0.6 times 3K plus 0.6 2I plus 2J plus 3K plus 0.6 times I plus 4J. And that's all over 1.8. And that's going to give us I plus 2j plus 2k. And so that's our location of G. We have to find the position vectors relative to the mass center. So our A prime is our A minus that. So we have 3k minus the I plus 2j plus 2k gives us negative I minus 2j plus k. For B, we have 2I plus 2j plus 3k minus I plus 2j plus 2k. That gives us I plus k. And then for C, it's just I plus 4j minus I plus 2j plus 2k. That's equal to 2j minus 2k. And we're going to multiply the mass by each of the velocity vectors to get the momentum. And so it's going to be 0.6 times 4j equals 2.4j. For B, 0.6 times I is 0.6 I. And for C, it's going to be 0.6 times 3k, so 1.8k. And I'll flip it over. HG is equal to R prime A cross the MAVA plus RB prime cross MBVB plus RC prime cross MCVC. And we just solve for all these, so it's just pretty straightforward. It's going to come out to 1.2 I plus 0.6 J minus 2.4 K. And that's 1.2 feet per pound second. All right.
What was K?
What was K? It was negative 2.4. All right. All right. I'll come back to this 14.39 if I have time. I'm going to move on to 15. Make sure we get a lot of this stuff. So for this problem, yeah, you guys can't see any of that. Okay. This distance is 400 millimeters. This right here is 150 millimeters. This is also 150, and this is 250. And this right here is 200. This is the y, x, z. We have d, e, I think c, a, and b. Okay. So this rod is going to rotate about a line joining points A and E with the constant angular velocity of 9 radians per second. Knowing that the rotation is clockwise as viewed from E, determine the velocity and acceleration of corner C. So looking from here along this line right here, it's going to be moving in this direction basically. So we're going to solve for the unit vector of EA to start with. So we're going to take this 0.4 squared plus 0.4 squared, which is this, plus 0.2 squared, which is this, yeah. And so EA is going to come out to 0.6 meters. So RC, and then RC relative to E is negative 0.4 I plus 0.15 J. So from here to here.
There's going to be a square root of that, all those squared, right? For your EA?
Yeah.
This is square root of all of that.
Of all these, yeah, to get this. And then so the unit vector of EA is going to be 0.4 I, or negative 0.4 I, plus 0.4 J, plus 0.2 K, all divided by the magnitude, which is 0.6. And that's going to give us 1/3 negative 2I plus 2J plus K. And that allows us to get a vector for the angular velocity. So we have 9 radians per second. We're going to multiply that by the 1/3 negative 2I plus 2J plus K. And it's going to give us negative 6 radians per second I plus 6 radians per second J plus 3 radians per second K. And then we have the velocity of C is going to be what we just solved for cross this, the position vector of C relative to E. That's going to be I, J, K, negative 6, 6, 3, negative 0.4, 0.15, and 0. So we get negative 0.5 I minus 1.2 J plus negative 0.9 plus 2.4 K. So VC is equal to negative 0.45 I minus 1.2 J plus 1.5 K. And let's see. Just gonna move up here really quick, or I'll flip it over. Anybody need that page? Or are you guys good? Okay. So the acceleration of c is going to be equal to the angular acceleration times that, but that's going to be equal to 0, plus angular velocity cross vc, which we just solved for. So AC is equal to 0 plus ijk negative 663 negative 0.45, negative 1.2, and 1.5. It's going to give you 9 plus 3.6i plus negative 1.35 plus 9j plus 7.2 plus 2.7k. So AC is 12.6i plus 7.65j plus 9.9k. All right, let's see, 1561. So here we're given this length right here, D to B, and this length from A to B. We know that this rotates the constant angular velocity of 1,000 RPMs clockwise. Determine the velocity of the piston P and the angular velocity of the connecting rod, so this, when theta is equal to 0, and this is, I don't know if you guys can see, this is theta right here, so when this is equal to 0, so when it's straight out, and then when theta is equal to 90. So we're going to start by converting the angular velocity, 1,000 RPM is equal to 1,000 times 2 pi over 60, gives us 104.72 radians per second. So at A, theta is 0 degrees. Position vector from B relative to A is 0.06 meters. So we have the velocity of B is equal to, or D, which is basically the piston, is equal to VB plus velocity of D relative to B. So, oh, sorry, getting ahead of myself. First we have VB is equal to position vector of B relative to A times the angular velocity. So we have 0.06 times the 104.72. So we have VB is equal to 6.2832 meters per second. So for here, for VD, this equation I just wrote out, we have that VD is equal to 6.2832 plus velocity of D relative to B. And at that point, they're all going to be in a straight line. So VD is going to be equal to 0, since this is going to be 0. We have that VP is equal to VD. So VP is equal to 0. And the angular acceleration of BD is VB over the length of that rod. So we have 6.2832 divided by 0.16 for 160 millimeters. And that gives us 39.3 radians per second.
Wouldn't VD with respect be negative 6.2832 to make velocity of D 0?
Yes. D respect to B when it's in a straight line. Yeah, it would have to.
Have to cancel out.
Yeah, they would have to cancel out. Yeah.
The velocity of D.
Yeah. Okay. Yeah, they cancel out. My bad. Okay. So for part B, do the same thing, but at 90 degrees. So we have B to A is still 0.06 meters, but it's straight out to the right instead of up top, which here it was up top. We have VB is equal to that position vector times angular velocity. So it's going to be 0.06 times 104.72. That's equal to that same value, 6.2832, but this time it's going to be moving down. And we have VD is equal to VB plus VD relative to B. We have VD equals 6.2832 down plus VD relative to B. It's going to be moving at some angle here. Let's see, so D relative to B at this point is going to be equal to 0 this time. Therefore, your VD is going to be equal to 6.2832 meters per second. And VD is equal to VP, so VP is 6.2832 meters per second down. And your angular velocity is the velocity of D relative to B over L. And so at that point, it's going to be equal to 0, since that's going to be 0 over L.
How do you know that at 90 degrees VD with respect to D equals 0?
Okay, so it's moving. This part right here is going to be moving clockwise.
Okay.
So here, let me try to draw a picture. You basically end up having this is D, and I think that's, yeah. not my ringtone. That was my alarm. Okay, I'll finish this up and then we'll take a quick break. Forgot that I actually had noise. All right, so at this point, I believe that there's something that's keeping it from moving. I want to say. The only thing I could think of is that it's just assumed that since it's moving clockwise, it can't move any farther past. It's gonna like move back the other way, because that piston would like fall out of that little slot right there. And
So like before it starts going back up,
yeah,
it's like 0 for a second.
yeah,
Okay.
that's the only thing I could think of based off what they gave us, because I can't think of any other reasons why they just make that assumption. But yeah, okay. We're gonna take a quick 10-minute break. So right at 10 minutes after this, at let's say 3:40, I'll start right back up again. I am going to stop about 10 minutes before the end of the session just to kind of wrap things up. Some stuff I have to do before you guys go, but I'm just going to cut to chapter 16 now, since I got like 40 minutes or so. So to start with, we're going to look at 16.6. This is very similar to one of the earlier problems I did, but just looking at some of the stuff we learned later on. We have 2,000 kilogram truck. It's being used to lift a 400 kilogram boulder. It's on a 50 kilogram pallet. Knowing the acceleration of the truck in the left direction is 1 meters per second squared, determine the reaction at each of the front wheels and the force between the boulder and the pallet. So we're going to start with Kinematics Approach. Acceleration of the truck is 1 meters per second to the left. And when the truck moves 1 meter to the left, the boulder and the pallet are each going to be raised 0.5 meters up. So we have AA is meters per second up, and AB equals 0.5 meters per second squared up. So we have the same thing here, 2T and the boulder. So the sum of the masses of the boulder and the pallet times gravity is equal to the sum of the masses times the acceleration. So we have sum of the forces in the y direction are equal to the sum of the forces in the y direction effective. So we have 2t minus ma plus mb times g is equal to ma plus mb times ab. And solving for t, you get 2320 newtons. And I'm not even going to try to draw this truck. Mt times g we have a F normal force on the front wheel and normal force on the rear wheel, and we have this force and tension. It's going to be equal to the mass of the truck times the acceleration of the truck. So we have for the truck, the moment at the rear wheel is equal to the sum of the moments at the rear wheel effective. So we have negative normal force at the front wheel times the distance from the front wheel to the back wheel, which is 3.4 meters, plus mass of the truck times gravity times 2.0 meters. That's the center of gravity right here. Minus the tension times 0.6 meters. So It's going to be up above the wheel. And it's going to be equal to MTAT times 1.0 meters at the center of gravity. So solving for that, we can find the normal force of the front wheel
It says MTAT what?
times 1.0 meters. And that's for going the y direction. So we have solving for NF 2.0 meters times the mass of 2,000 kilograms times the gravity 9.81 divided by 3.4 minus 0.6 meters times 2,320 newtons divided by 3.4 plus 1.0 meters times 2,000 kilograms times 1 meters per second over 3.4 meters. And that's going to give us 10,544 newtons for the normal force of the front wheel. And just flip back here. So, okay. Sum of the forces in the y is equal to the sum of the forces in the y effective. So we have normal force of the front plus normal force of the rear is equal to, or minus the mass of the truck times gravity is equal to 0 since it's not moving. And so plug in what we just found for the front plus NR minus the mass of 2,000 kilograms times 9.81 equals 0. And that gives us an NR of 9,076 newtons. And sum of the forces in the x direction is equal to the effective sum of the forces in the x direction. Force in the rear wheel minus the tension is equal to the mass of the truck times the acceleration of the truck. And solving for that, we get FR is equal to 2,320 for the tension that we solved, plus the 2,000 kilograms times 1.0 meters per second squared. And that gives us 4,320 newtons. So for the reaction at each front wheel, it's going to be 1/2 of the normal force of the front. So we had NF equals 10,544. So that divided by 2 gives us 5,270 newtons for each of the front wheels. And for each of the rear wheels, we have so it's going to be half of the normal force on the rear wheels plus, I believe, half of the force on the rear wheels from in the horizontal direction, which is going to be 5,030 newtons. And when you solve for that angle, it's going to give you 64.5 degrees.
thought we already solved for the forces.
We did, but we solved for, so, and this little diagram right here. So these are each of the wheels. I kind of did a hatch job, but so this is the normal force on the front and the normal force on the rear.
Yes.
So there's 2 front wheels, so you have to divide that normal force by the 2 front wheels.
So we solved for NR.
Yeah, but there's also FR. It's the horizontal force on the rear wheels. It's because that has to counteract the tension. So when you add those two, you have on the rear wheels, you have one force going that way and one force going this way. So you take the square root, or you square them both and add them together and take the square root of that. So it ended up being, what, 9076 divided by 2 squared plus 4,320 divided by 2 squared. And you take the square root of that, and that gets you 5,030. And it would be what the tangent, inverse tangent of the y over the x. So it would be, I believe, this value divided by this value. So if this is A and B, gives you the 64.5 degrees. And that. I'm going to come back to 1691 if we have time, because I can just tell it's going to be really hard to see, and I have a lot of questions still to go, so I'm going to put that right there. 1633. I don't know if you guys can read that. Okay, that's not too bad. So, flywheel has a radius of 20 inches, a weight of 250 pounds, and a radius of gyration of 15 inches. The 30-pound block A is attached to a wire that is wrapped around the flywheel, and the system is released from rest. Neglecting the effect of friction, determine the acceleration of the block and the speed of the block after it has moved 5 feet. So, I'm going to draw a quick diagram here of R. Alpha A and then we have, for the kinetics, at B we have BX, BY, and the weight, which is the mass times gravity, and that's going to be the mass of A times gravity. That's going to be equal to I alpha, and it's going to be the mass of A times the acceleration. So we have moment around B is equal to, or the sum of the moments around B is equal to the sum of the effective moments around B. And that is going to give us mass of A times G times the radius is equal to I alpha plus mass of A times the acceleration of the block times the radius. So we solve MAGR equals MPK squared A over R plus MA AR. So the acceleration is gonna simplify to the weight of A divided by the mass of A plus mass of the flywheel times the radius of gyration over the radius squared. So for part A, we have looking for AA. So we just plug in the values that we have into this equation that we just got. So we have 30 pounds over 30 over 32.2 plus 250 over 32.2 times, it's going to be 15 inches divided by 20 inches. And that is going to come out to 5.6615 feet per second squared. And it's going to be in the downward direction. For the velocity, I'm going to flip it over. So we have VA squared. This is just one of the earlier formulas. It's equal to VAO squared plus 2AA times the distance. I guess it's after it traveled 5 feet. So VA squared is equal to 0, since it was started from rest, plus 2 times the acceleration we solved for times the given 5 feet, and that's 56.6154. Take the square root of that and you get 7.5243 feet per second. All right. We have a slender rod of length L. It's pivoted about a point C, located at distance B from the center G. It is released from rest in a horizontal position and swings freely. Determine the distance B for which the angular velocity of the rod as it passes through a vertical position is maximum. B, the corresponding values of its angular velocity and of the reaction at C. I'll look for extra paper. Okay. So, position 1. Have v equals 0, angular velocity is 0, and T1 equals 0. Kinetic energy is 0. And then for elevation, the height is going to be 0. This is our base, so mgh is 0, so v1 is 0. And then at 2, we have, this thing's going to be straight up and down. We have A, G, C. This is our B length. The weight is pointing down, and B is here at the bottom. So our V2 is going to be this B times angular acceleration at 2. Our I is 1/12 m times the length squared. And our T2 is 1/2 mv2 squared plus 1/2 I angular acceleration at 2 squared. So it's going to be 1/2 times the mass of B squared plus 1/12 L squared times the angular velocity at 2 squared. Our height is going to be negative B so our V2 is going to be negative mgh, or negative mgb. So using the principle of conservation of energy, we have T1 plus V1 equals T2 plus V2. So this is all 0. So we have T2 is equal to V2. So 1/2 m B squared plus 1/12 L squared times the angular velocity at 2 squared minus mgb. So the angular velocity at 2 squared is equal to 2gb over b squared plus 1/12 L squared. So for the first part, we're looking for the value of b at the maximum angular velocity. So I'm going to take the derivative with respect to b. So we get b over b squared plus 1/12 L squared is equal to b squared plus 1/12 L squared minus b times 2b over b squared plus 1/12 L squared squared. And that's equal to 0. So solving for that, we get b squared equals 1/12 L squared. So b is 1 over the square root of 12. And the angular velocity, we're just going to plug that in to this formula we had here. And so we get 2g 1 over the square root of 12 divided by I think that says L squared over the square root of 12 plus L squared over the square root of 12. It's going to be equal to the square root of 12 times g over L. So it's going to be 12 to the 3/4 times the square root of g over L. And that's our W2. 1723. Two identical slender rods, AB and BC, are welded together to form an L-shaped assembly. The assembly is pressed against a spring at D and released from the position shown. Knowing that the maximum angle of rotation of the assembly and its subsequent motion is 90 degrees counterclockwise, determine the magnitude of the angular velocity of the assembly as it passes through the position where rod AB forms an angle of 30 degrees with the horizontal. So I'm going to say, start with the moment of inertia about B. It's going to be 1/3 the mass of AB L squared plus 1/3 mass of BC L squared. Draw a diagram. So we have B, C, A. It's 2, and then this is 3. So looking at position 2, we have that the theta is 30 degrees. So potential is going to be weight of AB L over 2 times the sine of 30 degrees plus the weight of BC times negative length over 2 cosine of 30. That gives, okay, we get that from WAB HAB 2 plus WBC HBC 2. And then kinetic energy is 1/2 moment of inertia about B times the angular velocity at 2 squared. That's going to be 1/6 MAB plus MBC L squared, angular velocity at 2 squared. And at 3, we have theta is 90 degrees. So we have V is weight of AB times L over 2. And the kinetic energy is 0. So using the conservation of energy, we have T2 plus V2 is equal to T3 plus V3. So plug this in for T2, MAB plus MBC L squared W2 squared plus WAB L over 2 sine of 30 degrees minus WBC L over 2 cosine of 30 degrees is equal to 0 plus WAB L over 2. So solving for the angular velocity, we have 3 over L times the weight of AB, 1 minus sine of 30 degrees, plus the weight of BC, cosine of 30 degrees, divided by the sum of the two masses. So we have 3 over 2 G over L, 1 minus sine 30 degrees plus cosine of 30 degrees. And that's 2.049 G over L, which gives us 50.25, and yeah, square root of that is going to give us our angular velocity of 7.09 radians per second. Okay. Have 8 minutes left. Don't know. Just gonna hop to. Yeah, you want me to touch on chapter 18?
I forgot. Paladin didn't do chapter 18, right?
Okay, so you guys,
No.
are you guys mostly PAL?
Yeah.
All right, so I'll focus. I'll keep on 17 then. You guys covered 17, right?
Just
Okay.
the first section.
The first section. Okay. I'll just do this 17, 18 then. Should be fine. Let's see. So we have a slender 9-pound rod. Can rotate in a vertical plane about a pivot point B. Spring of constant K equals 30 pounds per feet, and of unstrength length 6 inches is attached to the rod as shown. Knowing that the rod is released from rest in the position shown, determine its angular velocity after it is rotated through 90 degrees. So, I'm just going to draw a diagram here. C, B, G, and A. This is 12 inches, 7 inches, and 5 inches. And directly out from here is D. And this is 14 inches. This is our first position, our second position here. We have A, G, the weight, B and C. D. This will be 9 inches, 5 inches, and this is 7 inches. From B to D is 14 inches. All right. So position 1, we have, I'm going to look at the spring. We have x1 is equal to CD minus the unstretched length of 6 inches. It's going to give us 14.866 minus 6. gives us 8.8661 inches, or 0.73884 feet. So elastic potential is going to be 1/2 k x1 squared. So 1/2 30 pound per feet, 0.73884 squared gives us 5.25 pounds per feet. Or, sorry, 8.1882 pounds per feet. Gravity, we have Vg is the weight times the height, 9 pounds times 7/12 feet. That gives us 5.25 pounds per feet. So our total potential is VE plus VG. So 8.1882 plus 5.25 gives 13.438. And at T1, our T1 is going to be 0. At 2, we have x of 2 is 9 inches minus 6 inches equals 3 inches, or 0.25 feet. So VE is 1/2 kx2 squared. So we have 1/2 30 pounds per feet times 0.25 feet squared gives us 0.9375 pounds per feet. And for gravity, we have WH is 0 since H is 0. So our V2 is equal to 0.9375 pounds per feet. And our kinetic energy is V2. It's going to be the radius times.
What is VE that's really small?
It's 1/2 kx2.
No, the answer.
Oh, it's 0. It's the same as this, because Vg is equal to 0. So 0.9375 pounds per feet, or pound foot. And this is the velocity at 2, equal to the radius times the angular velocity. So we have 7/12 feet times angular velocity at 2. I is equal to 1/12 ml squared. So 1/12, 9 divided by 32.2 times 2 feet squared gives us 0.093168. So T2 is 1/2 mv2 squared plus 1/2 I angular velocity squared equal to 1/2 9/32.2 times 7/12 feet times angular velocity squared plus 1/2 0.093168. Yeah. And that's going to be equal to 0.094. Okay, I have time to finish this one. 4.138 angular velocity at 2 squared. So we're going to use T1 plus V1 equals T2 plus V2 is equal to 0. And so our V1 was 13.438, and that's equal to 0.094138 angular velocity at 2 squared plus 0.9375. So our angular velocity squared comes out to 132.79. Square root of that is 11.524 radians per second. And that is the answer. Oh, and it's going to be counterclockwise. All right, so that's going to just about wrap up the session. First, I want to thank you guys for coming, and I'd like to just ask if there's any important questions that you guys have first. I guess would like to ask you guys again if you guys could fill out the little reviews. That'd be very helpful. You can just leave them at your seats, and I'll collect them, and just make sure to clean up after you guys selves, and don't forget anything. And
Is the number we put in this 61?
I believe so, yeah.